Good afternoon to all. So myself Sanjeeva Reddy. So today we discuss about data structures and their classifications. So first of all, what do you know about a data structure? So data structure is nothing but the way of how we are going to storing the data and how we are going to access the data in a proper manner. So that is called it as a data structure. So when we are not going to storing the data in a proper manner, so it is quite difficult to access the data and it is not understand the complete meaning of the data. So we need data structure for effective storing purpose. Now, so we need to know what are the main classifications of the data structures. So there are mainly two categories of data structures. One is a linear data structure and the second one is non-linear data structure. So coming to the linear data structure, the first category of data structure, linear data structure, linear data structure. So linear data structure can be defined as the data structure in which we are going to storing the elements in a sequential manner, or we can say a linear order of elements. So then it is called it as a linear data structure. So what are the examples of linear data structures? So the examples of linear data structures are array, stack, queue, and linked list. So these are all few examples of a linear data structure. So first of all, array. So array can be defined as the data structure in which we are going to storing the elements in a linear order, sequential order. And we know that array can be defined as it is a homogeneous collection of elements. That means the same category of data type elements we are going to storing at one place. So then it is called a linear data structure. And we know that array indexing starts from 0 to n minus 1 and we can access that all the elements in a proper manner. So that is the information about array. So next, coming to the stack. So stack is also comes under linear data structure and the stack follows the principle called LIFO. So what is the meaning of LIFO? LIFO stands for last in, first out. LIFO principle. So now we will see how we are going to storing the elements in the stack. So we know that a stack follows the principle LIFO. Now we will see one example regarding how we are going to storing the elements in the stack. Okay, so stack is a linear data structure, right? So in the stack I am going to storing some elements. And one more thing, stack contains only one end, that end is called top end. So I am going to inserting elements at one end and I am going to deleting the elements also same end. So that is called it as a top end. So stack data structure contains only one end, that end is called it as a top end. So now we will see one example to understand briefly about a stack data structure. So now see here, so now this is a stack. So stack contains only one end, that end is called top end. So here in the stack we have some operations. So what are the operations of the stack means? Push and pop. These are all main two operations of the stack. So we have some other operations also. Peek, okay, is full. Next, is empty. So these are all some of the operations of the stack. Now we will see. So what are the operations with example. So now the stack is empty. So empty is nothing but there is no single element in the stack. Now this is the empty. So before inserting any element, what is the value of the top means -1. Top value should be -1 when means the stack should be empty, means there is no element in the stack. So then only it is called as a empty. Now what is the value of the top means -1. So now I am going to pushing. So pushing means I am going to inserting an element into the stack. So now I am going to pushing a 1 into the stack. Okay. So now what is the value of the top after inserting an element 1 into the stack? What is the value of the top now present? So for every insertion of the element into the stack, the top value should be incremented by 1. So before that -1, now I am going to inserting 1 here. So now the top value should be -1 plus 1. That should be 0. Now the top value should be 0. So next I am going to inserting one more element. Suppose I am going to taking a 2. I am inserting 2 here. So now the topmost element is 2. Now what is the, again the value should be incremented by 1, top value. So 0 plus 1 is nothing but 1. So like that, while inserting any element into the stack, the top value should be incremented by 1. So that is called push operation. Next, coming to the pop. So what is the meaning of pop operation? Is nothing but, so we need to delete an element from the stack. So that is called pop operation. So suppose 5, 4, 3. So now the stack contains 3 elements. Okay. Now I am going to performing pop operation. So while doing a pop operation, we need to delete an element which is the topmost element in the stack. I am not deleting the element 5. I am not deleting the element 4. It is not possible also. Why? Because the stack follows the principle called LIFO, means whatever the element you inserted last, that element only you should delete it first. So here first I am going to inserting 5, next I am going to inserting 4, next I am going to inserting 3. So now the 3 is the topmost element, right? So now I am going to deleting 3 first. Okay, next I am going to deleting 4, next I am going to deleting 5. So now in this stack, suppose I am going to performing pop operation, so the first element should be deleted, it will be third 3 element, next 4, next 5. So like that I can delete the elements from the stack. So next remaining operations will also be there. So peak is full is empty. So peak in the sense, what is the topmost element in the stack? So in this suppose 1, 2, 3, 4 like that we have. So now what is the topmost element here? So 4. So by using peak we can identify what is the topmost element in the stack. So what is the topmost element here? 4. So like that we can identify which is the topmost element in the stack. So next, what are the remaining operations we have in the stack? So E is full, E is empty, right? So why do we need a E is full operation and why do we need a E is empty? So E is full is nothing but, so we need to check the stack is full or not. So it should be completed or not. Is it possible to insert a new element or not? So we need to check. So that purpose we are going to using the operation called E is full. So we need to check the stack is full or not. So next coming to the E is empty. So we need to check the stack is empty or not. So that purpose we are using a E is empty. Next coming to the Q. So Q. So we already discussed about the stack, right? So stack follows the principle LIFO principle. Next coming to the Q. So it is also a linear data structure in which we are going to storing the elements in a sequential order, linear order. Okay, and here the Q contains 2 ends. One is the front end and the next one is the rear end. So this is the front end and this is the rear end. So now I am going to inserting an element at front end, then I can delete the element from the rear end. Okay, so one end I am going to inserting and then remaining end I am going to deleting an element from the Q. Okay, so Q contains 2 ends. One is a front end and a rear end. So here also, so similarly stack contains some push operation, pop operation like that. So Q contains operations called NQ, DQ like that. NQ, next DQ. So these are all some operations of the queue. So NQ in the sense I'm going to inserting an element into the queue at one end, and DQ operation, by using DQ operation we can delete an element from the queue at another end. So this is called a queue basic principle, FIFO. FIFO. So FIFO principle. So the abbreviation of this is first in, first out. So what is the element I'm going to inserting first? That element only we should delete first. Okay. So the real life example of queue should be any ticket buying, any movie theaters like that. So whoever the person will be in the first place, so that person only will take the ticket first. Yes. So that is a real life example of a queue. Okay. Next, coming to the stack real life example is, so suppose I am going to inserting 5 chapatis in the tiffin box. So whatever chapati I inserted last, that only I should eat first. So that is a real life example of a stack. Next. So next we will see about linked list. So linked list is one of the linear data structure. It is also comes under linear data structure only. So one of the linear data structure, linked list. So we will see what is the general form of a linear data structure, linked list. So linked list contains basically two parts. One is the data part and the next one is the next part. So here the data part is nothing but, so here we can able to insert any value. So suppose 10, 20 like that, 30, 40 like that. So and the next part should be contain next. So the next in the sense it should store the address of the next node. Address of the next node. So it is called the next part. So example, see here. So 10, 20, 30. Okay. So this is called it as a head node and this is called it as a tail node. Okay. So every node contains two parts. That is called a linked list. So these are all comes under a linear data structure. Now we will see non-linear data structure. So what is the definition of non-linear data structures? So the data structure in which we are not able to store the elements in sequential order. So if the sequential order means then it is called a linear data structure. If it is not in a sequential manner, it is not in a linear manner, then it is called as a non-linear data structure. So what are the examples of non-linear data structures? So the examples of non-linear data structures are trees, and trees and graphs. So these are all the main two categories of a non-linear data structures. Non-linear data structures. So first of all, we will see about a tree. So tree is nothing. Tree can be defined as it is the collection of nodes and edges, or we can say call it as a branches. So what is the example of tree means? See here. So see here. So this is the general representation of the tree here. So the one, so the node 1 should contains, the element 1 should contains, it is called it as a head node. Okay. And 2 and 3 are called it as a leaf nodes. 2 and 3 call it as a leaf nodes. So this is called so head node is also called it as a root node. So definition of the root node in the sense that is the starting of the node in the tree, that is called as a root node. Next, coming to the leaf node. So leaf node in the sense the node which should not contain any children, then it is called as the leaf node. Leaf node is also called it as external node also. Leaf node is also called it as external node also, means it does not contain any children. So now here one contains, the left children should be 2 and the right children should be 3. Okay. Now what are the some terminologies of the trees? So we'll see what are the terminologies of the trees. So first one, root node and the leaf node. Next, internal node. Next, depth. Next, height. Okay, so these are all some terminologies of a tree, non-linear data structure. So first of all, so root node, we know that, so that this is the starting node of the tree, that is called as a root node, or we can say head node. Next, coming to the leaf node, so here 2 3 call it as a leaf node. Why? Because 2 3 does not contain any childrens, that's why 2 3 are called as a leaf nodes. Yes. Next, coming to the internal node. So what is the meaning of internal node? In the sense, if the node should contains at least one children, then it is called as the internal node. So example, see here. So see here. So here we have, so total 5 elements. So the 5 should be called as a head node, and 6, 51, 26 are called it as a leaf nodes, and 7. So the 7 will be called it as a internal node. So internal node in the sense, the node which should contain at least one children, then it is called as a internal node. Okay, next coming to the height and depth. So what is the meaning of height? Height in the sense, the total number of edges from the bottom to that particular node, that is called as a height. Suppose see here, is there any edge from the bottom to this particular node 6? No. So the height should be 0 for leaf node 6. Next 51 also 0 0. Next coming to the 7, so this is the internal node, right? So it should contain 2 children, one is a 51 and the 26 is the right child, and this is the left child. So now what is the height of a 7? So height of 7 should be the number of edges from the bottom to this particular node. So how many edges are there from the bottom to this particular node 7? So 1. You can take right side. So from the bottom to this particular node, here also 1. Okay, we can check both the left side and the right side also. Next, what is the height of 5? Okay, 5 is the head node or root node. So what are the maximum number of edges from the bottom to that particular node? Okay, so see here. So what is the height of 5 means, we can say 2. Why? Because see here, from 51 to 7, 7 to 5. So the height should be 2. Okay. Next, coming to the depth. Depth in the sense, from the top to that particular node, from the top. So that is the reverse of the height. Okay. Okay, so 5. So this is the root node. So there is no any edge from the top. So the depth should be 0. Okay, and here 1 we can get. Okay, from the top to here we can get 1. And here 1, here we can get 2. So like that, these are all the some terminologies of the trees. So next we will see what are the classifications of the trees. So this is very very important topic, classifications of the trees. So we will see first one, binary tree. Second one, binary search tree. The third one, KVL tree. Fourth one, red black tree. Fifth one, plate tree. These are all some classifications of the trees. So now we will discuss the first three categories of the trees. First of all, we need to know what is a binary tree. Binary tree. So binary tree in the sense the tree which contains at most two children, then only it is called as a binary tree. At most two, not exceeded two. So we know that what is a tree. So see here, 1, 3, 4. Now here the root node should contains maximum two children. One is the left children, right children. Now this is called as a binary tree. Bi means two. At most it should contains two children. Suppose I am going to inserting one more element here, 3, 4, 5. Now this is not call it as a binary tree. Why? Because the one should contains the three children. It is not a binary tree. Okay. So that is a basic definition of a binary tree. So next, coming to the next category, binary search tree. BST. So it is also called BST. So this is completely different compared to binary tree. So how we are going to arranging the elements in BST? How we are going to arranging the elements in BST? So first of all, what is the basic definition of BST? Binary search tree. See here. This is called it as a binary search tree. Binary search tree is also called binary tree. Binary search tree is also called a binary tree because in BST also we have two children only, at most two children. Now see here what is called as BST. So 5 is the root and 4 is the left children, 7 will be the right children. So in BST, how we are going to arranging the elements means the left children should be less than the root and the right children should be greater than the root. Then it is called as a BST. Okay. So one example we can see. So 1, 2, 5, 4, 6. So we have 5 elements. Now by using these 5 elements, I need to create a BST. So what is the starting element here? 1. So 1 will be the root. Next I need to insert 2 here. So first we need to compare with root. So 2 should be greater than 1. So we need to insert at the right hand side. Next we can take 5. So 5, first we need to go for root. So 5 should be greater than 1 and greater than 5, greater than 2 also. Now we should insert at a left child of 2. Next I need to insert 4. So first we need to compare with root. Yes, it is greater than 1, greater than 2, but less than 5. So we need to keep as a left child to 5. Next we can insert 6. So greater than 1, we need to move right hand side. Next greater than 2, greater than 5 also. So we need to insert right hand side. So now this is one example of how we are going to generating BST by using these 5 elements. Okay. Next we will see what are the operations of a BST. So important topic, what are the operations of a BST? So operations means insertion, deletion cases we can see, and we can able to one more operation searching also. See here. So 5, 6, 1, 4, 3, 2. So these are all the elements. First we need to form the BST with this. So 5, 6, 1, 4 means 3. So first we need to compare with root, right? So 3 should be less than 5 and greater than 1, less than 4. Yes. Next coming to the 2. So first we need to compare with root. So it is less than 5. Next greater than 1. Yes. Less than 4. less than 3 also. Okay, so this is the BST by using these elements. Okay, suppose I need to search 6th element. So first we need to go for root. So 6 is greater than 5 means, so we need to find the location at the right hand side of the 5. Next I need to insert an element, a new element here. Suppose I am going to taking 9. How we are going to inserting an element, a new element here? So first we need to compare with root. So it is greater than 5. Yes, it is greater than 6 also. So I can insert here. So one more thing is, while inserting any new node, it should be comes under always at a leaf position. Inserting new node means. Next, coming to the deletion case, we have 3 cases. Deletion. So we will see one example. So see here. So deletion case, we have a 3 cases. One is the leaf node deletion, and the node which should contains 1 children, and the node should contains 2 children. Okay, so these are the 3 deletion cases in BST. Okay, so now I am going to deleting any leaf node. So how many leaf nodes are there in this here, in this BST? So 3 and 9. So we can simply remove it. Okay, now I am going to deleting 3 here. So this is the leaf node. Simply I can erase it. Now the case is the node which should contain 1 children. Okay, at that time you can replace either in order predecessor or in order successor. So we need to replace either in order predecessor or a in order successor. That is a deletion case which should contains 2 children. Okay, now this is the node which should contains only 1 children. Okay, now I am going to replacing 7 with 9. 7 with 9. So like that we can replace when the node should contains only 1 children. Now the question is, the node which should contains 2 children, then what, how can we delete that particular element from the BST? Okay, for that we can see one example. The node which should contains 2 children. So now I am going to taking 10. I am going to taking 10. So 10 should contains 2 children. One is 9 and the second one is a 14. Now I am going to deleting this. We can see the left subtree and the right subtree of a 10. So we have only one element here, 9 or 14. So while deleting the node which should contains 2 children, then we can replace it with either in order predecessor or in order successor. So what is the definition of in order predecessor and in order successor? In order successor in the sense, the right side smallest element of the deleted element is called as in order successor, and in LST what is the biggest element is called in order predecessor. So we have only one element, either left hand side and right hand side. So we need to replace 10 with either 9 or 14. Now how it should be? 7, 9, 14. 7, 9, 14. Now we can see 7 will be the root here, 9 will be the greater than 7, yes, and 14 will be the greater than 9. So now this is called as a PST. So this is how we can performing operations in PST. Okay, so insertion, deletion. So in deletion we have 3 cases. One is deleting a node with leaf node, deleting a node which should contains 1 children, and deleting a node which should contains 2 children. So this is called as a BST with the examples. So all BSTs are binary trees, but all binary trees are not BST. Why? Because in BST we have some logic. So all the elements are less than the root, and all the elements in the right hand side greater than the root. Okay, so all BSTs are binary trees, but all binary trees are not a BST. Next, coming to the next category of tree is the AVL tree. So AVL tree is called as a height balanced BST. It is not just BST, it is a height balanced binary search tree. How can we balance means? So by performing some operations called a rotation. So by performing rotation, we can balance the BST, then only it is called as a AVL tree. We have some four types of rotations are there: left rotation, right right rotation, and right left rotation. These are the 4 rotations we can perform in BST, which is not balanced. Then we can balance the tree, and we can check every node balance factor. So the balance factor value should be -1, 0, and +1. If not any of these values, then we can say it is a imbalanced one. So then we can perform rotation operation. By using rotation operation, we can do balance, then only it is called as a AVL tree. All AVL trees are BSTs, but all BSTs are not AVL tree. All AVL trees are BST only, but all BSTs are not AVL trees. So it is a balanced or not balanced. So that's why it is called a not vice versa. So this is some introduction part of data structures and categorization of trees, BST, binary tree, and AVL tree. So remaining trees we will discuss next classes. Thank you.